Hi there. Let's get some practice today naming binary ionic compounds. Now, it may be wise for you to have out this flowchart in front of you. You can find it on Canvas within the ionic naming unit. We'll also give you a copy in class, but this might be really useful to have in front of you. And as a heads up, we have already done this branch, the branch that goes straight down, binary covalent. This is molecular compounds, things that are put together with a covalent bond. For instance, an example would be carbon dioxide, CO2. And you'll notice that this is made up of two nonmetals. So today, what we're going to do is we are going to start talking about a situation when we have a metal and a nonmetal. And in particular, we're going to talk about when we have a cation and a single anion. So one cation, one anion, that would be two atoms. So for instance, sodium and chlorine. And they come together, and when they come together, there are two of them, so that's why we call this binary, bi meaning two. But you'll notice in this case, we are dealing with a metal and a nonmetal. And of course, when a metal and a nonmetal come together, we have an ionic compound. So now we're talking about ionic things. All right, let me join you on your note guide and we will dive in. So whenever you have an ionic compound, remember that ionic compounds are considered to be formula units because they are reduced down from the crystal lattices in which they exist. So for instance, in a covalent compound, you have formulas like this, C6H12O6. That would be glucose. And that is the correct molecular formula for the molecule glucose. That molecule sits by itself, and it's all good to go. But in an ionic compound, you might have a sodium ion here, and 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 I'm running out of room, right? But those all have a +1 charge. And then we might have interspersed in here our chloride ions. And it's starting to look a lot like Christmas, but that's okay. And you'll notice that I have here one chloride ion for every one sodium ion. Now, there are 5 sodium ions and 5 chloride ions, but in ionic compounds, we don't do this. The formula here is not Na5Cl5. The formula for ionic compounds is reduced. So the formula here is simply NaCl. And so that's what we need to do today. Because they're formula units, we need to reduce those charges. We are not going to keep them like this. In this case, they're not reduced. They are not simplified. But in an ionic compound, they are. So here are our rules. Now you can read the rules, but I think the best thing to do is actually just treat these as examples. And we'll go both from name to formula and also from formula to name. One little thing to keep in mind though is that we always, in this rule, are going to write the cation first. And remember, the cation is the metal. And conveniently, we read left to right, and the periodic table has the metals on the left and the nonmetals on the right. So that works well. Typically, whatever you run into first on the periodic table is going to be your cation because you see it on the left, and then the anion is on the right. So the naming structure here is actually going to feel very familiar to you because we are going to keep this first element the same as its name on the periodic table. So it might be a good time to pause the video and take out a periodic table if you don't have one already. But you'll notice Sr is strontium. And strontium is combined with F here. And so F is fluorine, but much like covalent compounds, we're going to change the ending to IDE. So this becomes strontium fluoride. And careful with fluorine, it actually is UO, not OU. Okay, aluminum oxide is number 2, right? We're going to keep Al the same, so that is aluminum. O is oxygen, we're going to change that ending to IDE. Number 3, Ag happens to be silver. Again, the cation just keeps its exact same name from the periodic table. The anion changes its ending to IDE. So this becomes silver chloride. Zn is zinc. And O is oxygen, so this is oxide. And in number 5, Ca is calcium. And Br is bromine, so this becomes bromide. Now, there's a question that all of us are probably asking, which is, if we remember active covalent compounds, we put prefixes in to indicate the number of each ion. So, there's a 2 right here. Shouldn't this be difluoride? Shouldn't this be dialuminum trioxide? Shouldn't this be silver monochloride? Shouldn't this be zinc monoxide, and this be calcium dibromide? And that's a really good thought if you're thinking that, and if you were covalent, you'd be right. But it turns out in ionic compounds, we don't need that because these are always simplified. So it turns out that the only way you can ever put together something like SR and F is with 2 Fs and 1 SR. So let's think about why that is. If you look at strontium on the periodic table, it's in the second column. That means that strontium has an electron configuration that ends with S2. So it has 2 extra valence electrons, right? So it wants to get rid of those. So that describes, as we've talked about already, why strontium always makes a +2 ion if it makes an ion. If it's an anionic bond, then it's making an ion. And that ion is going to have a +2 charge. Similarly, if you look at fluoride, or fluorine really, it's going to end with an S2. So there's its S2, and then it's going to have a P5, like so. Right, so it has this empty spot for an extra valence electron. So fluorine, when it makes an ion, it's always going to make F-1. And if you think about that, the only way to put these two together, a -1 and a +2, is to put 2 of the negative ones to match every +2, right? So that means we're going to have 2 Fs for every 1 SR, right? That's the only way their charges can cancel out. So you can predict these charges based on that. The same thing for aluminum and oxygen. Aluminum is always Al+3. If you didn't know that one, you can get out your whole year resources page. This is one of the ions that's given to you. Aluminum is always a +3 charge. Oxygen, based on its location on the periodic table, is a -2 charge. So if you want to have a neutral overall compound, what's the lowest common multiple of 3 and 2? Well, it's 6. So how many aluminums do we need to get there? Well, we need 2 of them, which is what we have. How many oxygens do we need to get there? Well, we need 3 of them, which is what we have. So it's actually best to think about these things by trying some on our own. So we're going to look at some names, and we're going to figure out what sort of compounds we make based on those names. So let's jump over here. Let's look at silver sulfide. So silver, turns out, is an ion, and it is Ag+1. That's another one on your whole year resources page. And I'm going to recommend that you do exactly what I'm doing here in blue and write out these ions above the names, and then we'll turn them into a formula over on the right-hand side. Sulfide, if you find sulfur on your periodic table, sulfide is S with a -2 charge. So if you think about how many of each one of those you need, you require 2 silvers to go along with every 1 sulfide. So you're going to have Ag2S. Calcium iodide. Calcium is Ca. Based on its location on the periodic table, it's going to have a +2 charge. That's something you'll need to be able to do, but remember it's just based on its column number. Iodide is in column 7, so it needs 1 extra valence electron, so it's I-1, which means we need 2 of those negative ones to cancel out the +2, right? So this becomes CaI2. Moving down the list, we've already said that calcium is a +2. Oxygen, or oxide, is O-2. So +2 and -2 cancel out directly. We are good to go with 1 Ca and 1 O. And we're done, right? Because their charges already cancel. We have a neutral compound. In number 9, sodium is Na. It has a +1 charge. Chloride is Cl. It has a -1 charge. Again, 1-to-1 ratio works and makes this thing have a balanced neutral compound. And finally, barium oxide, Ba, is barium, and it has a +2 charge. Oxygen, or oxide, is O-2. So again, one of each of those makes for a neutral compound, so BaO. And notice I'm not writing down a subscript for 1. It's assumed that if you don't have a subscript, there's one of those atoms. Now, there's a little trick here that you can use if you so desire, that we didn't discuss just yet, but you can try it if you'd like. It's called the crisscross method, and you may have already picked up on what's going on here, but I'm going to draw this in red. So you can, if you'd like, figure out these formulas by simply crossing these charges. So what do I mean by that? If we take this plus 1 charge, eliminate the charge part of it, just call it a 1, and put a 1 down here, and this 2 down here, we would get Ag2 S1. And look at what we get, AGS, or Ag2S. Right, so Ag2S1, as we predicted. If you cross this 2 down here, and this 1 down here, you'd have 1 calcium, 2 iodines. That's what we get. If you cross this 2 down here and this 2 down here, you'd get Ca2O2. But remember, ionic compounds simplify. So if you have 2 2's, those 2 2's can cancel out and simplify, and you're left with CaO. 1 Na down here, 1 Cl down there, right? Their charges become the subscript of the opposite atom. We're left with NaCl. We could get a 2 down here and a 2 down here, so we'd get Ba2O2, but again, those simplify to leave us with BaO. So you can do it either way. You can think about what charges you require in order to cancel out, or you can cross the charges like we've just tried there.